Hello
and welcome to Knowledge Track 4 on Digital Assembly. My name is Norman Maggi, and today I would like to demonstrate with this vehicle headlight how you can align different parts to each other and also how you can analyze them in an assembly. We already have the nominal data of the headlight. It consists of different parts, and every part has its own container in the software. An individual container offering space for a CAD, the measured data, and of course nominal elements, actual elements, and the inspections in between. Alignments are also saved in the containers. Here are a few examples as to what you can do. This diagram shows you where this light module is twisted and off-center in the housing. You might see this even better in this alternative visualization. A second option is, for instance, to digitally attach this cover to the housing. Also, in this visualization, you can see the distance between the cover's surface and its counterpart on the housing. Another option to visualize such a distance is by using curves, which has been prepared right here. These are two curves that have been compared with each other and depict, let's say, an actual state. I will show you how you get there with these examples. So let's get started with the first project. We already have two parts in this project, also shown in our software as two containers, the CAD from the housing and the CAD of the light module. Here I can load the corresponding measured values. That's the two of them. I can transfer them into the software using drag and drop and can clipboard them for the time being. Here you can see the meshes that have been measured. I'll display one in a different color. So you can see that these are two different meshes. I can hide and display both meshes separately from each other, and they have been scanned such that they are in one coordinate system, using joint reference points and thus representing a real structure. So this is exactly how they have been mounted in the headlight. The data of these two scans are now on the clipboard, and I can simply assign them to specific parts by using drag and drop by releasing the right mouse button. And now I can select that this part belongs to the container called housing. I can do the same with the light module. Now both containers have been expanded with the corresponding mesh data. Let's turn to the alignment. First of all, I align the housing to its CAD data and choose a pre-alignment for that purpose. The software automatically calculates the required shift to align it accordingly. Of course, what is still missing is the alignment of this light module. You could align it to its own CAD, but then this assembled state would no longer be there. For that reason, I want to proceed with the light module as I did with the housing mesh, meaning that it remains in its real-life assembled state. For this purpose, I can choose an alignment called copy alignment. And that's exactly what I can do. I can tell this mesh that I want it to perform the same shift, the same rotation as the housing mesh. Here I can select which alignment I want to copy, and here I can assign it to the part I selected. This means we still have the assembly situation between the two measured meshes, and both of them are aligned to this housing here. You can see quite clearly right here that the light module's data show a slight displacement. And in order to measure that displacement, I will first of all create a coordinate system for this part and use it to analyze the displacement and twist. I prepared a little measuring plan, which I would like to import. Also using drag and drop, and I will keep it at first on the clipboard. And then I can assign it to a part by saying add to part. And in this case, it belongs to the light module. I will now create a coordinate system from this plane as primary element, the orientation of the cylinder as secondary element, and from this cone I will create an intersection point as tertiary element. At first, all elements are transferred to the actual data using a measuring principle. In this case, our measuring principle is fitting element. And out of those two, I create an intersection point. I also want to create this intersection point using the nominal data. That is just the same way as I did right here with the target data. This is why the measuring principle is referenced construction. I can use these elements to create a coordinate system. The plane as first element, the cylinder axis as second element, and the point as third element. In the expert parameters, I can select that these data will be computed according to geometric dimensioning and tolerancing. And now I've tagged my coordinate system to this part. For better visualization, I will add a bit of transparency. Okay. This coordinate system is the nominal coordinate system created from nominal geometries. And by using the measuring principle, I can also create it for the actual elements. And here you see clearly that the two coordinate systems have a slight mismatch. I can now check this coordinate system, for instance the directions x, y, z, but of course also the direction of rotations, and see this body's orientation compared to its target data in the real-life assembly. You can also see this in the actual data, where I will increase the size of the coordinate system. You can see clearly that in the real-life assembly, the headlight is tilted forward with a deviation of 0.8 degrees and has rotated to the vehicle's body, the deviation being 1.7 degrees. Of course, you can choose a different orientation for this light module. I simply carry out a best fit by selecting all points of the element and by using its own CAD. Here I will select the cat is the light module, and maybe I can increase the distance slightly. Then you can see that the values have improved slightly, and as I click through the orientations, you can watch the part as it changes. Secondly, I would like to show you the positioning of this cover. I also prepared a project for the cover. Right here, you only see the cat of the housing and the pre-aligned measured data. And here on the reverse side, right here, this is where we want to attach the cover. We do not have any cat data for this cover. This means the data are aligned such that you have to connect the mesh of the cover with the mesh of the housing, and I will show you how this works. First of all, I need a mesh of the cover. So, in a parallel project, I will run a measurement series. Right here, I am using an ATAS ScanBox port. I already prepared the bottom of the cover and will now measure the top of the cover. The transformation into top and bottom is performed by joint reference points, which are visualized in both measurement series. You can see that part of the table is being scanned as well, but I can easily remove this by using a software function. Okay, by selecting the function cut out below plane, I simply select 3 points on the table, and everything below that plane is automatically cut out. As I said, I have already prepared the top, and in order to transform these two scans to each other, I will use joint reference points, which are visible in both measurement series. 1 point, 2 points, 3 points, and then I will let the software find all the other joint points for me. Okay, this mesh is ready to be polygonized. Polygonization is up and running. And I'll go back to my project to show you what I would like to do. Right here, we've got a bayonet lock, which means that the wedges of the cover go through this gap, slide across this area, and then have to lock into place in this little area. And we have 4 of them, evenly distributed. We finished polygonizing the scan. I will now export this mesh as a file. And I'll save it in my current project folder. You can see it right here. And again, I can pull the scanned data via drag and drop into my part project. I release on New Part. The mesh is automatically loaded, and I can also give it a name. In order to align this cover to the data, I will use the 3-point alignment. This means I will click onto 3 points of the housing data and 3 points on the data of the cover in order to have a rough pre-positioning. The picture-in-picture feature is quite helpful. This means I can display the data of the cover and in the other picture, I can display the data of the housing. Okay, I use the 3-point alignment and select the click-stop positions right here as points. This means the surface here, this is the click-stop position, where this specific wedge up here will lock into. The next click-stop position is here, with the wedge surface right here. And now the opposite side, where the point will be here. Okay, let's display my cover. Seems to have a really nice fit already. And seems to pretty well match the actual data of the housing. You can see right here that there's still quite a large gap. Coming to the next alignment, I would like to compute a best fit with tolerances. So I'll select all points of element, select local best fit with tolerances, and here I have the option to set the search radius for the best fit and to set the condition that the surfaces should not penetrate each other if possible. This is called condition outside target element. Here I can select for which target element I want to compute the best fit. In this case, I want to align it to the housing, and specifically to the target surfaces of the housing. And since the surfaces are opposite to each other, I can invert the surface orientation right here. Okay, this is the best possible orientation across all surfaces in question. Now, how can I display this distance between the parts? I will just create a distance. That is a surface distance. As always, I select the points to be used for computation. Again, I select all points of this cover, and under target element, I can select that I want to make a comparison against the mesh data of the housing. Here is the pool. The button already has been activated to invert the surfaces, since they are opposite to each other. Let's hide the housing. And highlighted in different colors, you can now see the absolute distances. And here I can see that the cover has about 0.5 millimeter of clearance, and here even 1 millimeter. Or you can look at the edge and its distance to the opposite surface. It is also interesting to check the wedge surfaces right here. Finally, I would like to show you a second option to analyze this distance. I already prepared a curve on the target data. That's the curve right here. And I already transferred this curve to the actual data by using the measuring principle. And, in turn, I would like to transfer this actual curve to the cover. Let me hide this. Okay, this is the curve. I create a second curve, in this case a projected curve. So I start off with this curve and would like to project it onto the cover, that is in the Z direction. And since the surfaces are opposite to each other, I will invert the surfaces. Now we have a pair of curves opposing each other, and now I can compute the distance between those two curves by creating a distance right here, that is a continuous curve distance. I select both curves, and can see right here that the software now shows the distance between them, actually for every point of the curve. As always, I can check this curve distance. Here it makes sense to do it in direction of the Z-axis. This means I can see the distance everywhere now, and I can attach labels accordingly. Now, if I look at the two meshes, and look at a section,
mir betrachte, dann wird auch schnell
you will
deutlich,
see pretty quickly what's going on. We have the two curves on the parts, in between the corresponding distance,
die Prüfung
and the inspection in orange on top.
drüber.
This was some information on aligning parts to each other and on analyzing them. Thank you for your attention.